It's possible to tap into the quantum realm, zero-point vacuum ether, and extract usable energy. This is the hypothesis we're going to be testing today from here in our garage using simple electronics, batteries, and coils of wire. Now, I know what you're thinking. Impossible. Science tells us this. There's laws. You cannot do that. But what if those laws were based on a box, and in reality, there's much more than what we currently think. This all-encompassing quantum realm is everywhere, in everything, and it's a dynamic field. It's not static. We can access it, and we can pull excess energy from it. Free energy, some might call it that, some might call it zero-point ether. It doesn't matter. The point being is that we can do usable work with it. So today, in this setup, we're using coils of wire. Now, we've talked about this before. If you put energy into a coil, pass electricity through it, it builds up a created electromagnetic field. When you shut off the flow of energy into the coil, that created electromagnetic field collapses. The faster you shut it off, the more violent that collapse is. We take this violent event, it's also called a flyback collapse, flyback energy. Now, when we put it into the battery, the interior of the battery has ions, electrolyte in it. These particular ones are lithium iron phosphate. You have lead acid batteries. There's many different types, but that's the point. There's ions in the battery, and we're smashing into it a very fast, violent collapse of energy. The theory, or our hypothesis, is that gradient, which is a rate of change, a sharp gradient, a sharp change between the ions and the flyback creates a dipole. It's a difference in the rate of speed, and this dipole creates an imbalance. Now, this imbalance must be corrected. This correction happens from the environment by pushing energy into the system. Our normal electronics operate on electrons. This imbalance is not being corrected by electron flow. It's something else. So it's a more fundamental principle. And that's all we're saying here. We're not saying physics and electrodynamics and science is wrong. It's just there's more fundamental principles going on, and that it needs to be updated. I know what you're thinking again. I know you're thinking like, how are you going to test this? How do you know how much energy's gone into the system? You can't just claim that. Well, we're going to be using this power supply here for our input. So all of the energy coming into this experiment is coming from this power supply. Now, it's very accurate. This is a $1,000 power supply. Thank you to our anonymous donor. We appreciate you for all of this equipment and everything you've done. This power supply allows us to measure exactly how much energy is being consumed by everything here. So we're taking into account all of the losses within the wire, losses within the coil, the power it takes to power the electronics. Everything is being accounted for by this power supply. We also have a secondary place to measure the amount of energy coming in, this watt meter here. So we have two double checks of the amount of energy coming in. Next question, how do you know how much energy is being produced? Well, we're using this little guy here, a CBAV battery analyzer. It allows us to very precisely discharge, do work with the energy within the battery. So we can discharge a known amount, watt hours or joules of energy. We've talked about joules and watt hours before. And then we can compare it with the amount of energy going in every cycle and coming out every cycle. Another couple important things that people will tell you, and they're correct, you should not measure battery's voltage while it is charging or discharging or any time close to that happening, because there's surface charges. It's just not accurate. So we're going to allow rest periods. We're going to do a charge through our coils. So we're pulse charging. We are then discharging with our CBAV battery analyzer, and then we're allowing a rest period, and we're going to measure the voltage after that rest period. So it's accurate. And then we're going to repeat, and we're going to do this over and over and over through the course of today, which, you know, is going to be 10, 12 hours. We're in the lab the whole time. We're going to repeat this experiment. So it takes approximately an hour and 10 minutes for us to do each one of these trials. We will pulse charge for 5 minutes, then we will discharge for 2 to 3 minutes, and then we will rest for an hour and measure our voltage. Now, again, I know what you're thinking. Voltage of a battery does not directly correlate to the capacity of the battery. We agree. We agree. So you need to run this experiment over and over. If you can pull enough energy out, voltage stays the same or increases, right? If we pull 5–10% of the capacity of this battery and the battery is trending upwards in voltage, well, that's a very high indication that there's excess energy coming into the system. So at the end of this experiment, or these series of experiments today, we're going to present evidence that either supports the hypothesis that yes, you can pull excess energy from the environment, from a more fundamental system than just the electron flow that we're taught in school as electrical engineering students or physics students, like I was 10 years ago when I got my applied science degree. Or it will support the null hypothesis. No, there's nothing new. Free energy is not possible. Everyone's correct. Just go back to sitting on your couch. Don't try anything new. So, You guys can take the evidence and see what you see, but let's get into the first experiment. This is real science, so, you know, science isn't all Iron Man flying around in the suit. You gotta put in the time and collect the data. That's what we're doing today. But again, I would say this is the very first time on this channel in over a year that we are presenting data to support our hypothesis, so that there is excess energy. And again, many different ways of doing this. This is just one of the ways. It's only one of the ways that we're working on this channel. We've got the rotor and the moving parts and the flywheel, totally separate systems. This is solid state, no moving parts, just demonstrating that in the batteries, something is happening. Let's get into the first test and start collecting that data and then take a look at it and see what it tells us. We're going to start pulse charging and you're going to see this voltage start to come up. So we'll turn on our system and you can see this is the voltage of the battery that we're charging. So we're charging this battery here, and then this is the voltage of the power supply, about 11.8 volts. The battery's at 13.2. And these coils here have frequency going through them. They're pulsing, collapsing, and you can see that our voltage is rising. So we're going to do this for somewhere, we're going to charge between 3 to 5 minutes. Our power supply is at 3.9 watts. Now, the wattage actually decreases as the battery fills up. So we'll just take it that it's at 3.9 watt. Again, we're removing experimental error there because we're taking the high end of the measurement. We could try and average it out, but let's just stay at 3.9 watts. You know, we're negating experimental error, which there is within all of this, right? There's experimental error in the measurements. We negate a lot of it by measuring the front end. We're not accounting for any of the losses in the system. We're trying to be as scientific as possible and take into account everything. So we will let this charge for 3 to 5 minutes, and then we're going to immediately do a discharge. The discharge will take out somewhere between 2 and 3 times more energy than what we put in with the charge, after which we will allow the battery to rest for an hour. So then it negates, if you try and take measurements right away after charging or discharging a battery, it's not accurate. You need to let it rest to get an accurate measurement. There's surface charges and there's just kind of a rest period where everything settles. So don't measure and think your measurements are correct if you do it right away or while discharging and charging a battery. You can see we started this test at 1:15. We're at almost 3:15, so it's been almost 2 minutes. And again, these first few runs, it's not likely to show much of a COP difference. The excess energy is not going to start flowing until we condition the batteries, get whatever effect happens in that electrochemistry going, and then it'll start to show that, yes, we're getting a lot more out than what goes in. All right, so now we're at a little over 4 minutes. We'll allow it to run for this test. We'll do 5 minutes. 5 minutes times 3.9 watts, even though you can see we're already down to 3.8 watts, so we're taking the high end of the measurements. 5 minutes times 3.9 watts, that's 0.325 watt hours of energy has been put into the system after we stop this test at 5 minutes. So we've got 15 more seconds, and then we will hit the master switch and turn it off and immediately start our discharge cycle. Okay, so 15, there we go. So we turned off the system. We'll just quickly pause this test, and then we'll move over to a new test, which is a discharge, and we're gonna discharge this battery. So you can see here, we're discharging. This is the watt hours of energy that has been discharged. We're at almost 1 watt hour. We'll discharge for somewhere, basically half the time of the input. So we charged for 5 minutes, let's discharge for 2 minutes or so. And again, we'll ease into these tests. If we start taking out a whole bunch on these first tests, it'll discharge the battery because it hasn't been conditioned. So we're at 2.6 watt hours. There, we're at 0.35 watt hours. So in under a minute, we've already taken out more energy than what we put in. If we run this for 2 minutes, much more than 2 times the amount of energy has come out than what we put in. But we'll take it easy on this test. Let's just take out a little bit this time. Let's stop here at 0.5. So we'll stop there. We took out 0.5 watt hours. Now we'll jump back over to the charge monitoring and just continue this on. So this charge monitoring test will run for 48 hours, and you'll be able to see these charge cycles, discharge cycles, and then where the battery voltage settles. And that's basically what we're going to do. We're going to do this over and over, over and over. This is what science is about, It's days in the lab collecting data, and that's exactly what we're going to do here. Let me show you what we've previously and where we're going to data log this. So some of the previous tests that we did, and we measure the battery charge, the rest time, the discharge amount, and then the rest time after, and then we take our final voltage measurements. Again, I know what you're thinking, and a lot of people will say this, well, voltage isn't a representation of battery capacity or the amount of energy in the battery. Agreed, but if we take out 10, 20, 30% of the battery's capacity and the voltage stays the same, that's a very, very high indication that more energy is coming out or going in than coming out. Is being able to do this where we have the two batteries. We won't use a power supply, and we'll cycle back and forth between the batteries. And that's what we have been doing over here on our machine, which we're gonna fire up. It's running beautifully with these battery banks, and our flip-flop there is flipping between the run and the charge and the run, with the intent of creating self-running systems that produce excess energy. So that's where we're going after this. Today's video, we're just gonna simply take some measurements. We'll gather the data, show it to you, and you can analyze it and come to your own conclusions, and we'll see whether it's leaning towards our hypothesis being null or true. So our hypothesis is that there is alternative energy to be harvested from the environment, and by using inductive pulse charging into batteries, the electrochemistry, that inductive flyback, it creates a gradient, a dipole that allows this energy from somewhere else to flow into the system. You can call it 0-point energy, free energy, etheric flow, vacuum energy, whatever you want to call it. I don't care. So these were our previous tests. We're going to erase the data from here, and then we'll start putting it in. So blue is where we started, and we started at 13.196 volts, okay? And we charged for a period of 5 minutes at, we'll call it 3.9 watts, okay? And again, we're taking the high end. We're taking all of the measurements so that it's on we're trying to be as real as possible here, right? I'm not gonna say, oh, it was 3.8. I'm not nickel and diming the measurements here. We're taking all of the high end stuff, so we negate as much experimental error as possible. The experimental error is in our favor if we're doing it this way. Now, we then rested for, say, 10 seconds because we went right to the discharge. And let's go back over here and just double check where our discharge was. So you can see our discharge was 0.515 watt hours. And again, notice the voltage starting to climb back up. So again, that's why we got to rest it. The voltage will climb back up to a stable point where we can actually measure exactly what happens. So our discharge, which we'll do in red, was at 0.515 watt hours of energy out, okay? And we did that in approximately 1 minute at 2 amps. So that's the kind of data we're collecting. We're now gonna rest 60 minutes, and I'll write down the voltage. I like to show the voltage that it pulled down to, because you can see once we do this over and over and over, it doesn't pull down as far. You can take more out and the voltage drop actually goes up, which is pretty cool. So let me just show you that here. So if you see right after that, we turned it on after the discharge, we were at 13.035 volts. So we'll throw that up here, 13.035. Okay, so that's what it pulled down to. And again, the more data that you can collect, it just allows you to go back, analyze it later, see patterns and things that you weren't necessarily looking for. More data, better, can't hurt. Collect as much data as possible, depending upon the starting and the ending point. So let's erase all of these old tests, get ready for a long day of scientific data gathering, science, applied science. It's like, showing the free energy device running and the moving parts and all of that is amazing, and that's what it's all about. But the bread and butter of science is this: collecting data over and over, repeating the results over and over, and then analyzing the data so that you can better yourself and your apparatus and conclude, your hypothesis. And again, it doesn't matter what you're doing, whether it's free energy experiments or any kind of science, collect data properly, right? Eliminate as many points experimental error as possible. And if you do have experimental error, make sure you account for it, right? Like, there's obviously still experimental error in this test. It's just we're negating a lot of it by putting it on the other side, right? We're making that null hypothesis as advantageous as possible to be achieved. So if it's not, then it means, we're leaning towards the fact that this is free energy, and we're showing an effect here that points to something more fundamental being present other than electron conductor flow, right? Another field that actually is the precursor to electron conductor flow, the 0-point energy field. Let's just take a quick look in this first test. So we started over here, 13.196. We're currently at 13.149. So maybe we won't quite get up to the voltage we started at on these first two. Maybe it'll draw it down a little bit. But the point being is that by the end of this, you can see we'll see how much energy is coming into the system. Okay, Okay, first test done. It's been an hour. You can see here, the voltage we started at was 13.196, and after 1 hour's rest, we're at 13.181. So 13.181 is less voltage than when we started at 13.196. Guess that means it's not for energy. I mean, we took out more than we put in, substantially, almost like 80% more. But I mean, I guess we should give up there, right? I guess it's not going to change. Or we can run it another 10 times and see what starts to happen as we do more and more and more of these tests. So let's do that. Okay, so let's see what happens now. We'll do another test. We'll do another run, another pulse charge. So let's start our timer, and then we'll switch on the system. Everything's pulse charging, and you can see the voltage is starting to climb again. We were at 13.181. We turn it on at 65 minutes, 0.54 seconds, and we'll let it charge. Let's do a 5-minute charge again, but we'll slow down the discharge a little bit so that it happens over a longer period. So we'll take out, say, we'll do 1.5 amp draw versus the 2 amp draw that we were at previously. And you can see again, we're at 13.909 watts. We'll be down to 3.909 watts. We'll be down to 3.8 or so. So we'll call it 3.9. It's well within experimental error. There you can see now right away, it's only the first few seconds. It's even above 3.9 watts. We're now down to 3.897 watts. So again, we'll do this. We'll do a charge, and we're going to discharge it, then we'll let it rest for an hour. We're going to repeat this over and over again over the next 10 hours straight, and then we'll see the results. Okay, so we started the test at 5 seconds. So as soon as it hits 5:05 on our timer, we will hit the main power switch and discharge away. Okay, so test is off. Now we will pause this charge monitoring so that we can do a discharge test. So we'll go new test and discharge, and let's go at 1.5 amp hours there. So we'll start the discharge, and we'll do 1.5 amps, not amp hours, 1.5 amp discharge rate from this battery. We're going to shoot now from here on out for the next 9 hours. These tests will shoot for approximately 2 times as much energy being drawn out as what we're putting in. We've gone beyond that in our tests. We've gone closer to 3 on a lot of them. The very final one, we'll do a bigger one just to show you the conditioning effect that happens here. Okay, we're coming up on 2 minutes here. All right, we will stop the test at 2 minutes. So we pulled out 0.651 watt hours, and then we'll go back over to our charge monitor and just continue that test, and we're going to rest. So on this particular test, we did 0.651 watt hours, and we did that at 2 mins at 1.5 amp. And then we're going to rest 60 minutes, and we'll measure our voltage again. And then as far as the input goes, we did exactly the same as on the previous one. And again, remember, our starting voltage was the ending voltage on the previous test. So our starting voltage here was 13.181 volts, and we did a 5-minute discharge, 3.9 watts. So that came out to 0.325 watt hours of energy that we put into the battery. We pulled out 0.651, twice as much. Now let's let it rest, and we'll see where we're at. All right, we're done. Another hour of rest. So we can check on our current test here. You can see this is the charge cycle, the discharge cycle, and we've allowed it to rest for 1 hour, and we are at 13.81 volts. It's just fluctuating. We'll give it another 30 seconds, and you'll see it level out at, we'll call it 13.181. This is how the energy comes into the system. You can see this real time here. We're just fluctuating between the last couple steps, and then it'll go steady up to 181. It would be advantageous for our next test if we called it 177, but again, we're going to put everything towards the null hypothesis at 1 hour. So it's been 62 minutes. So between 13.177 and 13.181. Okay, so there you can see it's leveled out, so it's at 13.181 again. 13.181, 13.177. We'll make a note of that just because it's, just barely at 13.181, but we took out slightly more than 2 times the amount of energy we put in, and it's come back to the voltage we started at. Let's collect our data. So we're at 13.177 to 13.181 volts. Right, very close to what we started at, 13.181. So we'll call it 13.181, and we're going to do the same thing again. We're going to do a 5-minute discharge at 3.9 watts, and again, that's slightly less than 3.9 watts It's slightly less than that, it's 3.85, but again, we're calling it 3.9 to keep everything fair. Let's do it again, let's do another test. There, you can see it's steadied out. Okay, so now we are going to, we're gonna turn on the power supply, and you can see that it takes 0.144 watts of energy just to power this little power meter. And then this device here takes all the electronics takes like another point. So there's 0.25 watts of energy being used just by the electronics minimum, plus all the losses. So just keep that in mind. Let's get our timer started. And again, we have a timer on the charge monitor as well, so we can verify it. I just like to use my, my clock on my phone here. So we're gonna flip the switch at 10 seconds. Okay, now we are charging. You can see the voltage rising. We're going up from 13.181. It's charging the battery. That's what it looks like zoomed in, and that's what it looks like. That's the tests that we're doing each test, and now we're going back up again. So we'll let this run for 5 minutes, do a discharge. And again, our input voltage is roughly 3.9. It starts out right around 3.9, slightly over, and then within 30 seconds, you'll see it's below 3.9 and stays closer to 3.85, 3.8 for the remainder of the test. So all right, we're coming up to the 5-minute mark. Remember, we started this timer at 10 seconds, so we'll go to 5 minutes and 10 seconds. And again, this would be one source of experimental error. You know, you could give it plus or minus 1 second on either side. Move to this. We'll stop the charge monitoring test, and we'll go to a new test, a discharge test, and we're going to start that right away. Pulling down the voltage, discharging energy, watt hours are being counted here. And we are at 0.54 watt hours. Since we drew we put in 0.325, so we want to put in at least 0.65, so we have double the amount of energy coming out than going in, plus all of the losses. So let's go right there, and then we'll restart the charge monitoring test, and we'll let it rest for an hour. I'll see you guys in an hour. All right, we're at the end of the third test. We've let the battery rest for an hour, and it is back 13.181 volts, and it reached that voltage much sooner. It reached it 5 minutes quicker than the previous time. So we took out a little bit more energy. We're at 13.181 volts. We're going to start the charging process again. Let's get everything ready. We'll start our clock, and then when it hits the 10-second mark here, we will initiate the on time. Okay, we're just about at 10 seconds. There we go. So the test is started. You can see the battery voltage begin to rise here. You can zoom in on it. There you go. You can see the battery charging now. And we're going to wait 5 minutes, do our discharge, record the results, repeat again. We're doing that another 6 times. It's 4 o'clock right now, 6 or 7 times. I'll stay up till a little bit later than my usual bedtime, till 11, to get this data and show you guys the difference between the starting and the ending. And once this battery is conditioned and has taken that charge, how much of a difference it is. Right now, we're discharging twice as much as we put in. We'll go up to 3 times as much by the end of it, and you'll see it doesn't make a difference, or much of a difference. 2 minutes. 5-minute mark here. So 5:10 on our stopwatch has been 5 minutes of charging, and we'll get ready to hit the switch. There we go. Now we will pause this charge monitoring test, go over to another discharge test, and start the discharge. You can see our discharge taking place, the watt hours that have come out of the battery, or joules, remember, 0.325 watt hours. And we're going to take out 0.7 this time. So that's like 2.1 times more energy coming out than what we put in. And again, we're also taking losses on the system with the powering the electronics and the coil voltage. So let's keep that in mind. We're just about at the 2-minute mark. So by the end of this here, we're gonna go to 3 minutes of discharge, and we're gonna try and get out 3 to 1, 3 times more energy than what we put in. Okay, so this one we will stop there, 0.648. So we'll record our, record the discharge and charge, extend our charge monitoring test. You can see 1, 2, 3, 4, so that's 4 hours. This is our 4th test, and this one drew down to 13.58. So now it's starting to do what I was mentioning before. These other two were at 13.047, and then the very first one was at 13.035. So it's drawing the battery down less every time, even though we were starting to take out gradually more and more and more energy. So something interesting. Let's let it rest. I'm gonna go record this. I'm not gonna keep recording all of the little bits because it's staying the same. We're not changing those variables. I just wanted you to be able to see the power taken, power in and power out, power in, power out. So our starting voltage on this one was the ending voltage on the previous one, which again was 13.181 volts. And so we'll start at 13.181 volts here. We discharged 10 seconds rest or we charged 10 seconds rest. Now we discharged 0.684 watt hours taken out. And again, our voltage that we drew down to was 13.058 volts. So you can see the voltage we're drawing down to every time is less and less and less and less, even though we're taking out more and more and more and more energy. It's kind of interesting. See you in an hour. All right, the end of test 4. And you can see we are at 13.181 volts where we started. And the 13.181 volt level was achieved 47 minutes, 50 minutes into the test. Previously, it took us 63 minutes, 59 minutes. Now it's becoming quicker and quicker when we get back to the same level. Soon we're gonna start going past the voltage that we started at. So let's get our timer. We will start our timer and then we're gonna pulse charge again at the 10-second mark. We're gonna hit our switch here, turn everything on. There we go, 10 seconds, everything's on. You can see we have our voltages for the power supply and the battery, our secondary power meter. Power supply up here is on. And the voltage on the charge monitor is increasing. We can zoom in there and see. So we've gone from 13.181 and we're climbing up. We're at 13.204. We'll let that charge for 5 minutes. We're gonna discharge for 2.5 this time. We're gonna keep increasing the discharge amount and we'll record the voltages. So our previous charge peaked out at 13.232. This current charge, we're at we're just going up, 224. So we're not quite there. We have 2 more minutes to go. And again, you guys can see up here, we're at 3.864 watts, but we're just calling it 3.9 watts. So we're not biasing any of the experimental error in our favor. We're biasing it towards null hypothesis, the opposite of our preferred hypothesis. Yes, we do have conformational bias, but we're aware of it. So I think conformational bias is dangerous when you're unaware of it, especially. Most biases are. Okay, so now we're at 13.228. And before we were at 13.232. So we're almost to the same voltage as before. We still have 1 minute and 10 seconds left in this charge cycle, this inductive pulse charge cycle, pulsing these coils with energy, letting the collapsing magnetic field go into the battery to charge it. There's the same voltage reached as the previous cycle, and we still have 30 seconds right now. So probably gonna see the same voltage reached in the charge phase. Now in the previous cycle, it was only reached for 20 seconds, so we have reached a higher voltage for a longer period of time in this cycle, so that's one difference we can note. We are gonna turn this off at the 10-second mark, and then we're gonna go directly into our discharge. So again, we'll stop this charge monitoring test, a new test, discharge, start. All right. Now we're going to discharge. We've taken out the same amount, or we've put in the same amount of energy every test, so we can record that. So this discharge, we want to take out, let's take out a little bit more this time. We'll go into the 0.7 watt hours. By the last couple runs here tonight, I want to take out 1 watt hour of energy, because that means if we put in 0.325 and we take out 1 watt, we have an excess of 0.775. What is that? Well, that is a 1% draw. 1% of the battery's capacity drawn out every single round. That's our goal. So we went 0.732, and then we'll go back to our charge monitor test, extend that, and let's see, where did we draw down to? 13.026. So we're drawing down less and less each time. There is a little bit of experimental error from me starting this test up again, the time, but it's relatively similar. So we're trending where we're drawing less and less down. So let's record our data. Okay, so the previous test ended at 13.181 volts. This test started at 13.181 volts. We removed the same amount of energy. We let it rest the same amount of time. And then we took out 0.732 watt hours of energy. And we drew the battery down to 0.062 volts. We'll rest 60 minutes and record the final voltage like we have every other time. So we're on our 5th test now. End of test number 5. Number 5 is completed. And you can see the battery voltage after an hour is at 13.181. Let's get back into it. Same thing again. We're gonna start our timer, and at the 10-second mark, actually we'll do it at the 5-second mark here. 5 seconds, it's on, we're running, it's going, and you can see that the battery voltage is increasing. At least I realized the microphone wasn't on halfway through. So again, we showed that the battery had reached the same voltage that it was previously at. We did our 5-minute discharge, and we're now pulling out the energy from the battery. We're gonna do somewhere around 0.8 watt hours this time. We're gonna try and get it up to 0.1 watt hours of discharge every time. So that'll be about 0.775 watt hours of excess energy being pulled every cycle from the battery. And why is that a good value for myself? Well, that's a 1% of the capacity of the battery being pulled out in excess every run. Okay, so now we're at 0.7. We're gonna stop here very shortly. Okay, and then we'll restart the charge monitor. So we pulled out, or we put in 0.325 watt hours again, and our starting voltage was again 13.181 volts. Our ending voltage was 13.181 volts, and we just pulled out 0.818 watt hours, I think. What was it? I got the 1.8 in my head. 808 watt hours is what we pulled out. Pulling out 2.2 times as much energy as we put in. So we'll wait 60 minutes and see you again. All right, 59 minutes later. This is the best test we've done. Why is that? Well, it's because we took out almost 2.5 times, 2.4, 2.5 times as much energy as we put in, and the battery voltage has increased beyond where we started, okay? Look at that, you guys. Now we're up to 13.188. So the battery voltage is increasing. We're taking out 2.5 times as much energy as we're putting in. It's pretty cool. There's a lot of other data in these graphs as well that we can go into after this, but let's just do it again. Let's do it again, you guys. You can see the battery is charging, and we're gonna do it for 5 minutes. And again, we're getting closer. Last time we took out 0.8. This time we're gonna take out 0.9, because 0.82 was not enough. It had more energy in there. It kept charging, so we gained a voltage, right? We wanna try and keep it basically, you know, at the same voltage. I mean, gaining's great, don't get me wrong, better than losing. You guys tell me, you tell me what other type of charging increases battery voltage and allows you to take out more energy than you put in. Like, there's no conventional battery charger that does that. So this evidence is supporting what Bearden said, what Bedini said, mainly Bearden. Bearden seems to be the most on point. People tell me that every person out there is a disinformation, whatever person, but maybe everybody is to some extent, depending on where they are in their journey down this path, or maybe a lot of these people were, depending on where they are in their journey or their intention, or who knows, I don't know. What Bearden is saying, the physicist, about this sharp gradient, this sharp collapse creating excess energy because of the ions in the battery, you know, lagging the electrons or that flyback voltage, who knows exactly how it works. I mean, to me, I like knowing how stuff works, but as long as I know how to build it and get the effect, I don't care, because all of this data, I know it looks insignificant, but this is just the starting point, right? This is a tiny little battery. Going up to these bigger batteries, these larger batteries, is going to produce a better effect because the plates are bigger. We're capturing that heavy side flow, that heavy side curl, the non-electron, non-conductor flow energy is what we're capturing. We haven't played with any of the variables. Any of the hard variables, like the R and the L values of the coils, the number of coils, series resistance, the voltages, those would be soft variables, like the frequency, the voltage, things like that. The hardware and the software has not been played with or optimized at all, and we're getting these kind of results. So Thank you to Julian Perry for open sourcing this. All of this circuit board is from Julian Perry. You guys can build it yourselves, right? You can look up Julian Perry. I put the links in the videos. Okay, we're almost done. This is now 2, 4, 6. This is test number 7 that we're starting. Thank goodness. Test number 7. And we are almost there. So what battery voltage did we reach? So we're getting to a higher voltage as well now, which is cool, and it's expected because we just left off after the rest period at a higher voltage. So now this charge is putting it at a higher voltage than before too. It's like, this is pretty incredible, you guys. I mean, I've done this before. This is the best test I've done in like running this an entire day straight, but these results are being replicated over and over and over. So 5:10, we're gonna switch off. There we go. The test is off. We will pause the charge monitor, go over to a new discharge test, and start the discharge test. So again, the last discharge test, we didn't take out enough energy. The battery voltage increased beyond where we started. Absolutely insane. I would say this is the first time in the last year, you know, that we're getting the proof, and I'm showing you guys evidence of excess energy. I'm not saying what we're doing here isn't moving towards it, and I'm not even saying that obviously if you can do this here, then you can do this on a Bedini motor. Somebody who tells you, like the Mythbusters, that, oh, they busted the Bedini motor, it doesn't put out more than in. It's like, well, what frequency did you run it at? You know, what duty cycle? What type of batteries? Like there's many different variables to optimize those. So I think the little Bedini motor at, you know, 50 hertz and a 20% duty cycle would probably come close to self-running, if not self-run, once you get the batteries conditioned, and or give them rest periods and flip maybe 3, 4 batteries. As far as our big machine here, I mean, I don't know what's going to happen. We're going beyond the frequencies that Julian Perry used. He kept the frequencies down at like 50 hertz, but we're going down the Paul Babcock path there, right? We're just trying to hit super high voltages and massive flyback spikes. Basically as many events as possible in a second. We're trying it all out. We're going to figure it out. Maybe both work. Like there's probably 100 different ways to skin this cat. I love cats. I have a cat. Do you guys got any animals? Let me know. Comment. Tell me what you guys are up to. I'm going to keep these videos going, you guys. I'm looking forward to the membership.io. Just to be able to interact with you guys and build this community, and it'll just be much easier. You can do weekly calls. You can chat with me 24/7, answer all your questions. You can answer my questions. We can just build a really nice community and work together. So let's stop it there, and then we will restart the charge monitoring. Okay, so 0.867 watt hours. I'll fill in this. And again, we took out exactly the same amount. We've taken out every single time 0.325 watt hours, but our starting voltage, I gotta go check what it was, but it was 1.188. Yeah, 13.188 volts. So we increased in voltage. So, oh my goodness, it wasn't even in line. Okay, so we took out 0.867 watt hours. We put in the standard 0.325 watt hours, but the voltage that we started at increased from where we were before. So those are the results I really like seeing. 13.188 volts. A higher voltage was achieved than what we started with while taking out 2.5 times the amount of energy we put in. All right, let's let it rest and then we'll run it again. Test number 7 is complete. All right, let's start the pulse charging again. 6, you can see the voltage is rising, and yes, we hit exactly the same voltage we started at. We hit the same voltage we started at, 40 minutes into the test. It's getting quicker and quicker and quicker to hit the same voltage. The energy flowing in is clearly increasing and becoming easier to obtain, or the effect is becoming stronger and stronger with the more of these cycles we go through. So, all right, that's 4 minutes, the same level we were in the last test. It will likely remain there. Okay, now we're gonna discharge. Okay, so now we're discharging. You can see the watt hours here. We're at 0.2 watt hours, 0.3 watt hours. So we got 2 more hours, boys and girls. Normally I'm going to bed in an hour. I like to get up at 5 a.m., but this is also very addictive watching this take place. So science is fun. It's a Saturday night. We'll live on the edge, stay up past 10 p.m. This one we're taking out 1 watt hour. Okay, so we're writing slightly smaller now so we can fit these last 2 tests in. We'll put 1.004 watt hours out. And we put in 0.325 watt hours. So we'll let it rest again, take the voltage, and we'll do that 2 more times this evening, and then I'm going to bed and we'll check the voltage in the morning. So. All right, end of test number 8. Back to the same voltage in 40 minutes. This test number 9, we're gonna start now. We'll get our timer going. Okay, we're gonna hit it at the 5-second mark. There we go, a little bit before. We're now pulse charging. Inductive pulse charging. You can see there the line indicating that we are charging the battery. I think this might be the last test for tonight, you guys. I'm getting tired. We do a solid 9, and we'll look at it tomorrow. Who knows, maybe we'll do some more tests tomorrow. It's just I wanted to do these back to back to back over the course of the day for you, and that's what this is. So test number 9. Oh, I'm so tired. It's only like 9 o'clock here, but 9:30, almost 9:30, it's 9:15, but when you get up at 4:30, 5 a.m., it catches up. We got a lot accomplished today though. In between we were building our boards. Cannot wait to show you that. This video might actually come out after I've showed you these on the machine. We're filming 2 videos at once here so we can kind of get caught up with content and get our feet under ourselves instead of always trying to film. It's a lot of work, you know. And the most important thing is this tech and building this tech. So that's why we kind of fell behind on the videos, just getting the tech proven. But now we're starting to get some results, starting to get our handle on it. We got the machine up and running. It's looking promising for 2026 to get this self-running machine. All right, we're ending almost there, and let's just see what voltage are we at. We're at same voltage as before. We've reached 13.236, same as the previous tests, 13.236, and we will turn this off at, maybe we should try this last test just a little bit longer. Maybe not, I already let it run past. We'll do it 5.5 minutes, and then I'll just calculate the difference here. Okay, so we did 5.5 minutes. We will stop test and do a discharge. So this one we took out 0.348. And right now we are at 0.87. Okay, we'll let it run to 3 minutes or so here. Okay, so that one we did 1.1 watt hours there, you guys, and then we'll run the charge monitor and we'll reconvene tomorrow. I've done enough of this for tonight. I'm not going to do it. All right, it's the next day. Where did we end up? Well, the battery voltage is at 13.204 volts. Now, it rested overnight, but when we started yesterday, this battery was at 13.196 volts. It had rested for several days, 13.196 volts. We are now at 13.204 volts. So that's like a 12-hour, 16-hour period later. So we're at a higher voltage than where we started, and we took out a total of a little over 7 watt hours of energy, which is like 10% of the battery's capacity. We then charged it with, say, 4% of the battery's capacity, 2.948. So basically 3 watt hours went in, 7 watt hours total came out, and the battery voltage increased. The first few tests, you can see this one here, we dropped in voltage. We took out, more voltage than we put in, like 1.7 times the amount of watt hours came out, but the voltage dropped. This one, the voltage almost dropped. And then now the third test, you can see the voltage is remaining steady. We're staying at 13.18 volts. We're taking out more than 2 times the amount of energy. Now we're up. So all from here, we're going more than the value of the COP value, more than 2 times the amount of energy out than in. Again, people will tell you, and they're correct, a battery's voltage does not denote, it's not directly correlated to a battery's capacity. I agree, absolutely. A battery and a lithium iron phosphate battery definitely doesn't have a linear discharge curve. I agree. But if you run this test enough times over and over and over and over, and you pull out enough energy and the battery's voltage increases, like you're moving towards, again, this is just evidence. We're gathering data. We can come to conclusions. We're going to keep, the more data that you have, the better. So draw your own conclusions, but we're getting excess energy out of the system by pulse charging this battery. Once we get down into these charges here, so you can see this one here, this test here, we increased from, we started at 13.181 and we're up to 13.188. So we're increasing in voltage and we pulled out more than 2 times what we put in. So we're starting to increase the voltage. These ones we stayed the same, and this last test here we put in 0.348 watt hours and took out 1.107 watt hours, and the voltage increased overnight. It basically stayed the same after an hour. So the thing is, we're increasing the voltage of the battery or staying the same and pulling out 3 times as much energy. Now, again, we talked about conditioning, so let's just clean up this board here quick. I've already logged all the data. We have everything stored on the computer, so we can erase this board. I need like 5 whiteboards. So by the end of that final test, we're taking out over 1% of the battery's capacity, right? Because it was like, it's a 76.8 watt hour internal capacity. We're taking out more than 0.768 watt hours every single test. So every single test we're taking out, we're able to take out 1% capacity. Now, is this commercially viable tech with those little batteries? Maybe if you want to like power, a little light bulb, because you could, bounce back and forth between the run and the charge battery, use multiple batteries. If you're taking out 1% of a battery's capacity, if we say correlated it to a 1 kilowatt battery capacity, that means that you could take out, 10 watt hours every test. And if you could we just did a test, we just demonstrated that you could do this once every hour. So you could do that 24 times a day, right? Once every hour, automate it. We were doing it manually, so that would be like 240 watt hours you could take out from a 1 kilowatt battery supply, right? So to power your home, you'd probably need, if you had 10 kilowatt battery capacity, then you could do 2.4 kilowatt hours, right? 2.4 kilowatt hours per day. It's not enough to power your home. That'd be enough for a little cabin for some lighting and stuff for sure. If you did 100 of these, then you'd have enough to power your home. But that's assuming that, that's as good as we get. That test, you could see as we condition the battery, it gets better and better and better. You can pull out more and more and more energy off every test, and you don't need to wait those rest periods either. So imagine if we could take it so you could run one of those every 30 minutes. Or imagine if we could get it up so we could draw out, say, 2% of the battery's capacity every test. Or what if we could get it up to where we could drop 5% of the battery's capacity, right? Then it's not taking that much. Then you're getting from a 10 kilowatt supply. If you're at 2%, you can get 5 kilowatt hours a day. If you're at 4%, you can get the battery's capacity out every day. To power a home, you need somewhere between 20 to 30 kilowatt hours a day roughly for an average sized home. So, is this possible to power your home with no moving parts? Well, start stepping this up with our custom built silicon carbide electronics. Again, everything we did today was just this most simple, basic setup you could possibly do. We haven't optimized any of the variables, right? There's the There's all the hard variables. So the hardware, the coil size, the size of the wire, the R and the L values, the number of coils, things like that. Then there's all the soft variables, the frequency, the duty cycle, the voltage, all of these things, the rest periods. We didn't even touch that, and we're getting a 1% draw capacity every test. Even as is, technically, you could still, self-run some stuff. Is it going to be super efficient? No, you need a bunch of batteries flipping around. But as soon as you increase it to 2, maybe 3, 4, 5%, then this is extremely commercially viable tech. And the point being is, I thought they said that there's nothing coming into the batteries. I thought Bearden was wrong. I thought we're nuts for thinking that there's more to science than electron flow. Well, let's just keep going with this. Obviously, the next step is we're going to flip between the run and the charge battery and make a little self-running system. So that's where we're at. I hope you enjoyed this video. Remember, there's limitless potential in all of you, all of this technology. Don't let people tell you that things are impossible. Get out there, build with your hands, you guys. Keep going, because that's what we're doing here on this channel. I cannot wait to show you this machine over here, self-run, because it's going to do it as well. And again, just keep this in mind when people tell you Bedini motors and stuff can't self-run. It's like, well, we just showed you that you can get excess energy out of the batteries. So what frequency do you need to set your Bedini motor at? What duty cycle do you need to set it at with your batteries in order to make it self-run? Think about it. I love you all. This is Limitless Potential Technologies. You guys contact me. My contact info is in the channel. I can't wait to share with you the membership in the next video. We're going to launch membership.io, and it will allow us for a place to work together and explore this tech, science. I can share my ability to prototype everything. Anything you guys want, you can help me build this membership platform up and allow me to provide value to you. Again, we can do weekly calls, direct messaging. The platform is incredible. I've already paid for a year's membership. It's going to be amazing, you guys. Look forward to this future, and I love you all. I'll see you soon.